Hey, today we're going to be doing the following proof question, and I'll read it now. So it's asking us to prove that for all integers n greater than or equal to 1, the sum of the first n odd numbers equals n squared. And then it says that is, prove that 1 plus 3 plus 5, so the sum of the first n odd numbers all the way up to the nth odd number, which is 2n minus 1. That equals n squared. So I'll just write, this is the nth odd number. So we're trying to show that if we add up the first n odd numbers, we get the same thing as just doing n squared. So because our question was a statement about all positive integers n or all natural numbers n above some number, we're going to be using induction to prove it. So the principle of mathematical induction is for when we want to prove statements that have in them for all natural numbers something is true. The principle of mathematical induction is telling us that when we want to prove these statements, it suffices to do the following two things. So the first thing we need to do is show that the base case holds. So if we look at the very first instance of the statement where we're looking at 0 or maybe 1, if our question starts at 1, we need to verify that that very first instance of the statement holds. That's our base case. And then the second step is the inductive step. So this is kind of where the induction happens. What you do is you take k to be some integer that's between the starting point and n, and you have to show the following implication statement. So we need to show if p of k holds, then p of k plus 1 holds. Why is it true that if we're trying to prove a statement of this form, we just need to show these two things? Well, if we first show that the base case holds, so if we know 0 holds, and then we also know the inductive step, I know that if p of 0 holds, then p of k plus 1, so p of 1 holds. So that means I can go to the next one. I know that the statement for 1 is true, and then I can keep doing this over and over again. I know 1 is true, so I can show 2 is true using the inductive step, and so on and so on, and so we can get any positive integer the statement holds. Another thing I want to mention is because the inductive step is an implication, so we need to show this implication statement. When we prove implications, we assume the if part and we try to show the then part. So when we're showing the inductive step in these types of proofs, we want to assume p of k holds, or p of k is true, and we want to show p of k plus 1 is true. So that's how we're going to structure the proof. Okay, let's go back to our question. Right, so in this case, p of n, the thing we're trying to show is the statement, the sum of the first n odd numbers equals n squared. We're trying to prove p of n for all n. And another way of writing that is how the question gave it to us in more formal math form, is 1 plus 3 all the way up to 2n minus 1 equals n squared. So when I'm writing my proof, I'm going to start and say we're going to do this by induction. And according to the principle of mathematical induction that we looked at earlier, the first thing we have to do, step 1, is the base case. So the base case is that we check that p of 1 holds. So what would p of 1 be? Since we're starting at n equals 1, p of 1 is the statement, the sum of the first 1 odd numbers equals 1 squared, right? But if I'm doing the sum of the first 1 odd numbers, that's just the first odd number, 1, is equal to 1 squared. This is the thing that we're trying to check. So is this actually true? Yes, it is, because 1 squared is actually equal to 1. So we verified the statement p of 1, and so we verified our base case. So this is true, and our base case is done. Okay, next step. So the next step in the proof is the inductive step. And remember, the inductive step is saying I assume p of k is true, and I want to use that to show p of k plus 1 is true. So I'm going to assume p of k, which is the statement, the sum of the first k integers, k odd integers is equal to k squared. So assume for k between 0 and n, that 1 plus 3 plus all the way up to the kth odd integer, which is 2k minus 1, is equal to k squared. And I've gotten this just by looking at our original p of n and plugging in k wherever I see n. So this is something that we're assuming, and we're going to use it to prove the statement for k plus 1. Whenever I'm writing a proof, I like to write down what it is that our goal is, or what it is we're trying to show, just to keep that clear in my mind. We want to show that the sum of the first k plus 1 odd integers, so 1 plus 3 plus all the way up to, so the sum of the first k integers is this sum here, and then the next odd integer is whatever this is plus 2, right? Because I add 2 to get the next odd integer, so that would be 2k plus 1. So I'm trying to show that this is equal to k plus 1 squared, right? So on the left-hand side, I've got sum of the first k plus 1 odd integers. And on the right-hand side, I've got k plus 1 squared. So this is the statement p of k plus 1. This is what we're trying to show. And we're going to show it using our assumption that p of k holds, so using this assumption. So if I'm trying to show this equality, right, I could maybe start with the left-hand side and try to show that it's equal to the right-hand side, right? And at some point I'm going to have to use my assumption, my inductive hypothesis is sometimes called, my inductive assumption that this is true. So I'm going to have to use this. Let's start by rewriting the left-hand side of the thing we're trying to show, the equation we want to get to. So 1 plus 3 plus 2k minus 1 plus 2k plus 1. So that's the left-hand side, and I want to eventually show that it's equal to k plus 1 squared. But if you notice, if I look at the sum of the first k plus 1 odd integers, the sum of the first k odd integers is already part of that sum, right? If I look at just up to here, this is the sum of the first k odd integers, right? And then here's the k plus first odd integer. So I already know by assumption that the sum of the first k odd integers is equal to k squared. So I'm going to use that assumption. So this sum here is equal to k squared by our inductive hypothesis. And then I still have 2k plus 1 at the end. So this is by inductive hypothesis. Again, where we're trying to get to is to show that the expression we have right now is equal to k plus 1 all squared. And if we factor this expression, or if you multiply out this right-hand side, if you expand this out, you'll get that these are actually the same. So if we factor k squared plus 2k plus 1, that's the same as k plus 1 squared. Right? If I look for two numbers that multiply to 1 and add to 2, I get the numbers 1 and 1. And so I could rewrite that as k plus 1 all squared. So we've just shown the equality we were trying to show. So that means by the principle of mathematical induction, the statement we were originally trying to prove is true. By the principle of mathematical induction, I'll just write it as PMI, the original statement that the sum of the first n odd integers is n squared is true. So that completes the proof. We can draw our little square at the bottom right, and we're done. Congrats, you just proved your first, well, maybe it wasn't your first, but you just proved a question using mathematical induction. I hope this video helped you better understand mathematical induction and how to prove statements using induction. And yeah, see you later.